right, good morning, everyone. Hope you guys had a nice weekend. I want to start off by just going over the calendar for these next 2 weeks leading up to spring break. See if you guys have any questions. Okay, so we're pushing the topics back by 1 day because initially I had antiderivatives being today, but we didn't get to curve sketching last Friday, so we'll be doing the curve sketching worksheet today. Tomorrow, your assignments 1 through 4 are going to be due through Teams, and it's going to be worth 10 points each. So all these assignments leading up to spring break is going to total to be a quiz grade. So if you just turn it in on time and go through and show me your work, you'll get full credit, and it's going to should be an easy 100 on the quiz. But even if you turn in late, or if you turn in all the assignments late, if you do everything they're supposed to, you're still going to get a 90. So it's not going to, I didn't penalize you heavily if you're turning in late, but I also want to give some incentives for you guys to turn in on time. Okay, so due tomorrow by midnight, I'll send out a text remind tomorrow afternoon for that. So tomorrow we're going to also start our second semester topics with antiderivatives. I want to start off by going over a specific type of free response questions that we haven't seen yet. So these are going to be antiderivative word problems. So I want to start off with that. It's a popular type of free response topic on the AP exams. So I want to kind of get you guys kind of used to that type of a format. And then on Wednesday, we'll probably do more of a traditional antiderivatives, like solving integrals, whether it's power rule or U substitution or long division or synthetic division. So working through all the different variations of integral rules. And then Thursday, I hope to put together a quiz review worksheet. And then that quiz is going to be on next Thursday. Okay, so Thursday, I think we're going to be virtual. So we'll go through that worksheet, and then I'll also have assignment for homework that's going to go towards your quiz 1 grade. Friday is going to be asynchronous day. So class, there's no attendance taken that day. But I think I still want to have class sessions for any students who just wants to come in for me to go over the previous night's homework, or want me to work through some problems, or just getting more additional review over homework or over the quiz material. But I'm not going to cover anything new. I just want to be available during class periods for to go over any material. But I'll record those sessions, and again, don't have to attend that day. I'm not covering anything new. I'm just going back and doing some going over some homework that some students may find to be beneficial, but again, you don't have to come to class that day. I'm going to have a help session in the afternoon, in the morning, for any students who need a help session for the Chapter 7 recovery. So I returned most of your test grades to you, and I hope to give back your test, especially for the students who are looking to potentially do recovery. So I'll return those tests to you so you know what to do corrections on. Hopefully today or tomorrow I will have the details of the Chapter 7 recovery assignment. Okay, and then that Chapter 7 recovery test will be next Monday, either morning 7:15 or afternoon 4:30. Tuesday is going to be asynchronous day. It's ACT day for juniors. But I may, after school, after 3:30, I may have just another help session for the quiz that's coming up on Thursday. Wednesday, we'll have a class period to do a quiz review, and then Thursday will be your quiz. And then Friday, your last set of assignments are due, assignments 9 and 10. And then I may make assignments 5 through 8 due on Tuesday as well. Okay. Any questions with these next 2 weeks? All right, let's look at curve sketching, derivative graphs, and particle motion. Hey, so we're starting off with curve sketching. We're really not going to do a whole lot with actually sketching the curve. It's more gathering information about the graph, right? With first derivative test, we're going to be able to gather information about where the graph is rising, where the graph is falling, where there's a relative max, where there's a relative min. For concavity test, we're going to go to the second derivative function, gather information about points of inflection, where the graph is concave up, where the graph is concave down. And then we're also going to talk about the second derivative test, which is basically another method of finding max and mins. But instead of sine lines, we're going to use the second derivative function to make a conclusion about that critical point, whether it's a relative max or relative min. So let's start off with the first derivative test. We're going to use f prime to determine locations of relative max, relative min, as well as intervals of increase and decrease for the original function of f of x. So first step is finding f prime, because f prime is going to be where we're going to be looking for these places or these characteristics of max, mins, and increase, decrease. From there, we're going to find critical points by setting the numerator and the denominator of f prime equal to 0. Okay. Sometimes you may not have a denominator. If you don't, then just set the numerator equal to 0. The reason why we're looking in the denominator location as well is because your denominator location is going to give us where slope is undefined, which could be a sharp turn, which could end up being a max or min. So we don't want to miss out on that opportunity. And then the second thing is we may be seeking out places where slope is undefined, meaning it could be a vertical asymptote or hole. So even though a vertical asymptote and hole has no chance of being a relative max and relative min, we still want to, if they exist, we still want to place them onto our sine line because they will help separate our intervals of increase and decrease. Okay. All right, so let's look at number 1. At what value of x does our function have a relative minimum? So relative minimum, we know that's going to come from first derivative. So we'll just go right into it. F prime equals. Our function is nicely set up for power rule. We can go and apply power rule. No need to make any adjustments. X becomes 1. 2x to 2/3. We bring the 2/3 down. Subtract 1 from the exponent. 2/3 minus 3/3 is just negative 1/3. Clean this up here. I get 4 over 3x to the 1/3. Now notice I have some split fractions here, so if I find a common denominator, I'll be able to know exactly, have more clarity in terms of how to find my critical points. So I'm going to find a common denominator. My common denominator is going to be 3x to the 1/3. So we have numerator and denominator clearly identified. We'll set both equal to 0 separately. We'll add 4 to both sides, divide by 3, cube both sides, and we can solve for x. So I get x equals 4 cubed, which is 64, over 3 cubed, which is 27. And then over here, divide both sides by 3. And I just get x equals 0. So I have 2 critical points. So they're going to go onto my f prime sine line now. I'm going to choose values in each interval to test. So I'll choose -1 here. I'll choose 1 here. 64 over 27 is a decimal value that's slightly less than 3, so I can choose 3, or I can choose something a little bit higher, like 4, to make it a little bit more obvious what the sign is going to be. All right, now what do I test this against? Do I put this into the function f of x or into f prime?
F prime.
Good. All right, f prime, because we're still in the information gathering stage. We still want to know whether each of these intervals is going to result in the positive or negative slope. So yeah, goes directly into f prime. I'm going to put it into the cleaned up version there. -1 in for x. I get -3 minus 4, that's positive. Sorry, -3 minus 4 is negative over a negative, so negative over negative is positive. So positive, I'm going to associate with a positive slope. Right. Insert 1 in for x. I get 3 minus 4, that's negative, over 3. So negative over a positive is negative. Insert 4, 3 times 4 to the 1/3. That's going to be a value a little bit greater than 4, so that's positive. Over positive, so 2 positives gives me positive. The problem is asking for relative minimum, so we see that there must be a relative minimum at 64 over 27 because we see the slope go from decrease to increase. Okay, any questions with 1? Okay, so a little bit of review into the first derivative test. Okay, moving on to concavity test. Our procedure is going to feel very similar. It's just that now we're doing everything from the second derivative standpoint. So we're going to set f double prime equal to 0. We're going to find critical points by setting numerator and denominator equal to 0. We're going to place critical points onto our f double prime sine line, and we'll test points in each subinterval. But now the difference is that the information that we're gathering is a different set of information, right? We're not gathering information about max and mins. We're not gathering information about the curvature, where there's a point of inflection, where there's a concave up, where there's concave down. So this is what we're after, right? We're after where the curvature changes from either concave down to concave up or vice versa. And we're looking for a point that resembles this physically on the graph. Okay. So number 2, the graph has a point of inflection at, so anytime we're looking for point of inflection, we know it has to come from the second derivative function. So we have to work our way down to our f double prime. Okay, so let's find f prime first. Our equation is nicely set up for power rule, so go through power rule. From y prime, we can find our second derivative, power rule again. We can set our second derivative equal to 0. We can also factor GCF out. And then we can solve for x. Okay. Now, can we stop here and say that these are points of inflection? Not yet. Okay, so that's an important point that I want to bring up. I think it's easy for us to stop here and say, well, these are my solutions, so these must be points of inflection. But what I want to remind you is that these are, right now, these are point of inflection candidates. Okay, but they have not yet been confirmed. And then in order to confirm, we have to go through a sine line. Okay. So there's a step that I left out under in the directions here. So number 3 says place critical points onto our second derivative sine line. Test each point on each subinterval to determine increase and decrease of concavity. I mean, a concave up or concave down. So I have a fourth statement here. So we're going to determine and find our points of inflection by looking to see if f double prime changes signs at these critical points. So we have to go through our sine line now. On my sine line, I'm going to place these candidates, 0 and 1. And we'll choose values in each subinterval. So I'll choose -1, I'll choose 1/2, and then I'll choose 2. All right, and where do I insert them into? Y double prime, because we're gathering information about concavity. So they're going to go into the second derivative function. Okay, I like to put it into the factored form. Allows us to quickly gather information about whether it's positive or negative. So -1, and for x, I get negative times negative, which is positive. So positive second derivative is going to associate with concave up. 1/2 in for x, positive times negative. It's negative. That associates with concave down. Plug 2 in, positive times positive. Okay, now can we confirm that these are points of inflections? Yes. Okay, there's a change in sign. That means 0 is a point of inflection. At 1, there's also a change in sign, so also points of inflection. All right, so how do I find the physical locations of these points of inflection?
I'll plug into the original.
Into the original, right? Now that we're looking at, now that we know that we've identified the x value, we want to look for the location in terms of the y value. We can insert them back into the original function. So 0 minus 0 is 0. 1 in for x, I get 1 minus 2, which is negative 1. Okay, any questions? All right, so I want to keep stressing this because I've seen on enough practice AP tests where you may find all these critical points, but enough students make that jump without testing that they're purposely going to have some critical points not end up being points of inflection. So for instance, something like this, right? If I have my critical points, but I realize that there's no change in sign, then it's a critical point, but it's not a point of inflection, right? There must be a change in sign in order for us to make that jump, that conclusion, confirming that there's a point of inflection there. Okay. So moving on to second derivative test, which is essentially the same results from applying the first derivative test. But let me talk about the procedure here. Okay, we're going to use the second derivative function to determine relative max and relative min, very much like how we would do it with the first derivative test. But the initial step is going to look the same. We're going to find f prime. We're going to set f prime to go to 0. We're going to find our critical points, just like how we would. But this is where the two methods is going to feel different. With the original first derivative test, we would go to a sine line, right? We'll create a sine line, just like how we did with example 1. We'll test values, and then looking at the arrow changes, we can determine whether there's a relative max, relative min. This is the method that most of us prefer, and it makes sense. It's just more visual. But with the second derivative test, rather than putting it into a sine line or creating a sine line, we're going to take these critical points that we found, and we're going to insert them into the second derivative function. And then based off of the results that we get in return, we can conclude whether that point is a relative max or whether that point is a relative min. So the way we do that is after we insert into the second derivative function, we look to see what value we get. Is it a positive or is it a negative value? If we get a negative value in return, we know that it's producing a negative second derivative value, which means that the graph is part of a concave down graph. So if the graph is part of a concave down graph and it's part of a slope 0, we know that point must be a what? Relative what? Relative max, right? Relative max. But if my second derivative value produces a positive number, then that graph must be concave up because that's what positive second derivative is associated with. And if my graph is concave up, there must be a relative what? Relative minimum. Okay. So let's look at example 3. So this is a problem where even if you try to go through first derivative test, you're not going to have enough information. You're going to have to rely on second derivative test to conclude whether there's a max or min. So let's look at the statements provided. It says f prime of 5 is equal to 0. Now, can you put into words, what does that mean?
The slope at the x value 5 is 0.
Okay, so means the slope is equal to 0 at x equals 5. Now, if the slope is 0, do we know whether it's a max or min? No, right? It's too vague, right? So right now, this is what we made. These are the possibilities, right? It could be part of a relative min. It could be part of a relative max. It could be neither. Okay. So, I mean, maybe it could be sitting here. It could be sitting up here. It could be just at a flattening out place where it's neither a max or min. So right now, we still are, kind of in the dark in terms of which category that it falls under. So this is where the second statement is going to help us out. Okay, it says f double prime of 5 is equal to -3. So we know we have some more additional information about what's happening to around this point to help us narrow down which relative extrema we're looking at. Now, what does this mean? F double prime of 5 is equal to -3. Right. Good. So you look at -3, you know -3 is less than 0. So anything less than 0, we're going to associate negative second derivative with concave down. And if my graph is concave down, that means my graph is going to look like this. And if my graph looks like this along with slope 0, I can conclude that there must be a what? Yeah, relative max. F double prime. Okay, let me point out two issues that kind of throw students off a little bit. One issue is, I think sometimes students get to this point, they're looking at this negative value, and they don't know what to do with it, right? What if it was -5 or 10 or 20? What does that mean? And the important thing is that we don't care about the numeric value. You just want to know whether it's positive or negative. That's all we care about. So if we can just look at that number and just associate it with, okay, that's either one or two, that's in category 1, right? That's in my negative concavity category. And so don't worry about what that number is. Just, categorize it as positive or negative, right? That's all we need to know. So that's one thing. The other thing is, I think it's easy to get mixed up, right? If you're just relying on the words, I think it's going to be, you're going to be thrown off. But because if you look at these words, right, I think we tend to associate concave down with relative minimum, because down and minimum, they kind of sound like they're similar in terms of wording. And then you would associate concave up with the relative max, because it sounds like up and max, they both sound the same. So I think the way to, so that we don't make that confusion, is draw out the picture of the concavity that you're dealing with, right? If you can visually convince yourself what concave down looks like, then you can also convince yourself that you're not looking at a relative minimum, you're looking at a relative maximum, okay? Same thing, right? If you're seeing concave up, you want to associate concave up with a parabola that opens up, and then looking for a slope 0, that must be a relative minimum. So just be careful of that. If you don't draw the picture out, you may run the risk of just associating the words, those words together, and you may make the wrong conclusion. Okay, any questions there? Okay, let's go to the next page. We're moving into the derivative graph, F prime graph. So we need to be able to look at a derivative graph and be able to gather information about the original function. So from the F prime graph, we're going to gather information about the original graph in terms of where does the original graph exhibit relative max? Where does the original graph have relative minimum? Increase, decrease. Where does the original graph have point of inflection? Concave up, concave down. Okay. So here are the steps. If we're looking at an F prime graph, we have to understand that that is not the original function. Okay. So if you're just picking out relative max, relative min, increase, decrease, treating it like as if it's the original function, everything's going to be off. Okay. So we're going to create a slope sine line to kind of help us kind of bridge that information between the derivative graph and the original graph. And the way I like to start the process is, as a reminder, I like to label the regions above the x-axis and below the x-axis as either positive or negative slope. I like to use up arrow and down arrow so I can visually remind myself, okay, I'm looking at, that's how I'm going to be picking out relative increase and decrease. And then we want to also identify the x-intercepts of the F prime to be potential max and mins. Okay, so those are the critical points. Okay, so we'll focus our attention on the F prime sine line. We're looking at an F prime graph. So if I want to gather information about the original graph, I would like to kind of give myself some visual reminders. Above is going to represent positive slope. Below is going to represent negative slope. So here's my F prime sine line. I'm going to start off with my endpoints. So from -4 to 7. So where are the critical points that we can place onto our slope sine line?
First -1. Slope 0.
Well,
oh, this is the graph.
Yeah, this is F prime. This is F prime graph.
So that -2.
Okay.
And 1.
And 5. Good. All right. So we're looking at the x-intercepts. The x-intercepts is where our slope zeros are going to occur. Slope 0 in terms of the value, right? Is not in terms of the actual slope, right? We can't pick these values out. That's something else. Okay. So -2. 1 and 5. All right, so we identify these x-intercepts. Next up, we want to assign each interval as either positive or negative slope. So what do you see between -4 and -2?
Positive slope.
Yeah, the location is above the x-axis. We're going to associate location as positive slope because it's above the x-axis. I think the confusing thing about this is you're looking at this going, wait a second, that doesn't look like positive slope, it's decreasing. Well, the decreasing indicates that the slope is becoming less, less steep, it's becoming more gradual. So you have a slope of 2, followed by a slope of 1.5, slope of 1, slope of 0.5. These are all different variations of positive slope, right? It just means that the slope is kind of flattening out, but it's still maintaining a positive slope all the way through. Okay, what between -2 and 1? right? Below the x-axis, so negative slope, okay? Okay. Between 1 and 5, all this is positive because it's above the x-axis. And then from 5 to 7, it's still above the x-axis. So we have two sets of positive slopes. Now the arrows are going to be extremely helpful to us because we know where the graph is increasing of the original graph. And we also know, based off of these arrows, where the relative max is going to occur and where the relative mins are going to occur. So we're not going to look at this picture for now. We're just going to rely on the slope sine line to help us fill out these intervals or these characteristics. So interval of our function increasing, we're just going to seek out the positive arrows. And the reasoning is because f prime is greater than 0. Positive slope. Interval decreasing. We just have one interval decreasing, right? From -2 to 1. Relative max. Relative max is where my slope goes from a positive to negative.
So -2.
And our reasoning is because f prime changes from positive to negative. Relative minimum, we see we have one relative minimum, right, at x equals 1. Bless you. Okay, so that's everything that we can gather from our slope sine line. Okay, questions there? Okay, moving on to our second derivative sine line. Now we're going to be picking out the peaks and valleys of our f prime graph. These are going to be locations of our points of inflection. And then we're going to determine intervals of where our graph is rising and falling. Wherever our f prime is rising, that's going to correspond with concave up. Wherever my f prime is falling, that's going to correspond with where my original graph is going to exhibit concave down. So where do we start?
-1.
Okay.
Oh, -4.
Yeah. Endpoints first. And where are the points of inflection off of the f prime graph?
-1. 3 and 5.
Good. All right. Now, this is not where points of inflection look like on the original graph, right? On the original graph, points of inflection are usually the steepest points on the graph, where the graph is kind of reaches its maximum steepness before it's kind of levels off. And then so the max and minimum steepness of a graph is indicated by the peaks and valleys of your f prime graph. So we want to be able to categorize our intervals as either concave up or concave down. So what do you notice between -4 and -1? Decreasing. So if my f prime is decreasing, that's going to correspond with concave down, right? Because definition of concave down is where our slope is becoming more negative. So as long as it's moving towards a negative direction, visually our graph is going to kind of resemble that concave down shape. Okay. Between -1 and 3, positive slope, so that's going to correspond with concave. What? Oh. 3 to 5, negative slope, concave down. 5 to 7, positive slope, concave up. Okay. Populating the sine line is going to make it easy now for us to fill out these statements about points of inflection and concave up, concave down intervals. Intervals of concave up. We have 2 intervals, right? -1 to 3, and then from 5 to 7. Our reasoning is because f double prime is positive, greater than 0. Concave down. We have 2 intervals of concave down. Okay, questions? Okay, next we're going to move into particle motion. Particle motion is motion along the x-axis involving position function, velocity, and acceleration. So what I want to show you with particle motion is that it's virtually the same thing that we did with first derivative test and concavity test. We're going to find f prime. We're going to create our f prime sine line. We're going to find critical points by setting f prime to go to 0, and then we're going to populate each interval with positive or negative. Same thing with the second derivative function. It's just that we're calling everything with a slightly different name, and our context is going to be different. Instead of f prime, we're going to call it velocity function. Instead of increasing and decreasing, we're going to call it positive or negative, and we're going to associate positive velocity with moving to the right, and we're going to associate negative velocity with moving to the left. Okay. We're still going to find the second derivative function, but instead of calling f double prime, we're going to call it acceleration. We're still going to set second derivative equal to 0, but instead of calling it where that's the point of inflection, we're going to say that is where acceleration is 0. And then instead of concave up and concave down, we're going to say, oh, positive means positive acceleration and negative is negative acceleration. So same process, we're just calling everything with a slightly different name. Okay. So part number 5. The position of a particle is moving along a line given by s of t, for t is greater than or equal to 0. So that's our domain. Our domain is from 0 and then positive values after that. For what value of t is the speed of the particle increasing? Okay. So let's think about what that means, right? Speed increasing. How do we determine?
Both velocity and acceleration signs
have to match. Okay, so we're going to have to look at both velocity and acceleration sine lines. We're going to have to compare the sine lines because we want to look for where there's going to be that matching sign. So either they're both positive or they're both negative. We want it indicate the full intervals where velocity and acceleration have the same signs, because where velocity and acceleration have the same signs, that is where our particle speed is increasing. Okay. Likewise, if I'm looking for particle speed decreasing, then I'll have to look for opposite signs. Sorry, I underlined the wrong thing here. This here, we're looking for speed increasing. So we want to identify where velocity and acceleration have the same signs. But we're going to gather information first, right? We're going to find a velocity, create a velocity sine line, find acceleration, develop the acceleration sine line. We'll line them up and see where we see the intervals having the same signs. Okay, so velocity function first. That's the first derivative. Our position function is nicely set up for power rule, so no need for adjustment. Jump directly into power rule. We set velocity equal to 0. Look for critical points, just like how we would if it was f prime. I can factor a 3 out. Multiplies to be 7, adds up to be -8. Here's our velocity sine line. We know that 0 is a starting point, so I'm going to have 0 as the first value, followed by 1, and followed by 7. Okay, test points in each interval here, so 1/2, 2, and 8. Insert into the factored form of my velocity function. 1/2 in for t. I get 1/2 minus 7, that's negative. 1/2 minus 1, that's negative. 2 negatives gives me positive. So I know that in this interval, the object is experiencing positive velocity, which means it's moving to the right. All right, let's see what happens at t equals 2. 2 minus 7 is negative. 2 minus 1 is positive. Negative times positive is negative. So the particle is going to stop at t equals 1. It's going to turn around and start moving to the left for the next 6 seconds, between 1 and 7. All right, let's see what happens at 8. 8 minus 7 is positive. 8 minus 1 is positive. 2 positives gives me positive. So the object is going to stop again, turn around, and start moving to the right after 7 seconds. All right, so we have our velocity sine line. Let's see if we can gather information from the acceleration perspective. So to find acceleration, we have to find the derivative past velocity. So we go through power rule again. 3t squared becomes 6t. 24t becomes 24. Set acceleration equal to 0. Factor 6 out and solve for t. T is equal to 4. Create your acceleration sine line. Again, 0 starts. But there's only one critical point, and that's going to be 4. Choose values in each interval here. I'll choose 1. I'll choose 5. 1 and for t. 1 minus 4 is negative. So negative acceleration exists between 0 and 4. Plug 5 in. 5 minus 4 is positive. Now we're looking for where velocity and acceleration have the same signs. I think to make it easier, I'm going to line them up so I can see exactly where they're going to have the same signs. So 1 and 7. Four. All right, so I lined them up as best as I could. Can you identify the intervals where you see velocity and acceleration having the same signs? Yeah. Right, between 1 and 4, we see that velocity and acceleration are going to be lined up. They're both going to experience negative signs, which is one of the conditions for increasing speed. They have to have same signs. And then from 7 to infinity, we see that they're lining up again, but now they're both positive signs. Good. So we can say increasing speed. On the interval from 1 to 4, and then from 7 to infinity, because velocity and acceleration have the same signs. All right, any questions? So hopefully today you'll get a chance to do the homework worksheet that's associated with this topic, and then get all that finished so that you can turn everything in by tomorrow. Assignments 1 through 4, 3 teams. I'll send out a reminder tomorrow afternoon so you guys can get all that in. All right, that's all I have. Hope you guys have a great day. See you tomorrow.